Hello. Today I would like to give you a summary of the most important parts of the mathematical background of reliability engineering. This is very important for the understanding of most of the parts of this lecture. Okay, let's start with the reliability function. So we have a certain number of devices which come into existence, and over time the number of surviving devices goes down. So when we call the number of survivors lowercase n, then on that basis we can also describe the different parameters of reliability. So here n is the survivors and capital N is the initial number. So the reliability is now defined as n divided by n. The complementary of the reliability function is the failure function. You could also say it's a failed portion, and that's just 1 minus r, or you could say if you measure in percent, 100% minus reliability in percent, and so that's the failed portion. Then we have the so-called density function, in German Dichtefunktion. For instance, that's a bell-shaped function in many cases, and here we derive the failure function by time, and we get the first derivative of this. But that is not yet the failure rate. When n is the size of the starting sample or the number of specimens which came into existence, that is an important parameter, but in many cases we just do not know this number. For instance, we do not know how many cars are really driving in the roads. We can only know how many cars were produced, but if that's the cars which are operated, we don't know for sure. When we take the derivative of the survivors by 10 and by time, and we divide it by the numbers existing at that time, that is the failure rate. We could also transform the formulas, and you say it's the f of t derived by dt divided by the reliability, because reliability is the surviving portion. Or you could also say, to make it more simple, the failure rate is just the density function divided by the reliability. but the density function is just minus reliability derived by dt. Okay, here we see the reliability goes down with the number of specimens that survive, and on the other hand, the failure function goes up in a complementary way. These are, let's say, the general differential equations, but of course these formulas can be also applied to specific formulas like the exponential equation or the Weibull equation. Okay, there is another parameter which is the mean time to failure. And normally, how would you determine mean time to failure? You would just say, okay, I take a certain time interval over which I measure the times from beginning to failure of all specimens. The longer I test, the more I get to the true value, but I will never be able to test until infinity. So, addressing the reliability function again, you could also say we have several specimens. Each specimen has a lifetime of her own, and now summing all of these lifetimes up gives us a total time. And then we divide this by the number of specimens. We get the mean time to failure. On the other hand, when we know the function over time, then we could also take an analytical approach. For instance, what we could do is we take the integral over this curve, so that's the area under the curve, and here we can either integrate reliability over time, or we can integrate time over reliability, but here we need analytical description of the function. So in fact, we can say we take the area and we divide it by the half width between 0 and 1, and here we get the mean time to failure where the blue line is. So it's the integral from 0 to infinity of reliability function over time, and we divide it by the width of that curve, and that's just 1. And in that way we can say the mean time to failure is generally the integral of reliability function from 0 to infinity over time. And if we know that function, for instance as a Weibull or an exponential function, we can form this integral in an analytical way and we can calculate the numbers. So what functions do we have for r of t and f of t? You should also know these for the exam. The simple form is the exponential equation of an exponential function, and it says f of t is 1 minus e to the power of minus lambda t, where lambda is the failure rate, and in this case lambda should be constant. The second important curve is the Weibull function. Of course, depending on the parameters of this equation, we can have a different behavior of the failure function over time. So it can have some kind of lag until it increases in a progressive way, or we can have something like an initial linear increase, but finally the slope decays and we approach 100% of failures. When we speak in a more general way, when the failure rate is not constant, we call it with the letter h of t. Okay, but this we already know. Okay, here I have taken the derivative, and when we take this formula for the exponential function, then we see that this is just minus lambda times e to the power of minus lambda t divided by r of t, which again is e to the power of minus lambda t. So e to the power of minus lambda t cancels out, and we end up with a lambda, and that lambda is constant. Now we go to the Weibull function. You should also know the Weibull function. That's one thing. The other thing is you should know how we find the Weibull function for a certain device, for instance. So how we would do a test in order to make a Weibull analysis. So the Weibull function is f of t is 1 minus e to the power of what? Minus t divided by tau. And then we also have an exponent, which we can call beta or b. And that exponent shows us how the behavior of that function over time is. What's the meaning of the time constant? The time constant is just the inverse of the failure rate in the case where that exponent beta is just 1. So you could say the time constant is the inverse of the failure rate. And in that case, the time constant is the same like the mean time to failure. Also, we can look for the time constant, and when the failure function has a value of 0.63 or of 63%, that point of time defines the time constant of our failure process. You can test it when you say the time is just the time constant, and at that time you end up the f of t is just 1 minus 1 divided by e. E is 2.7, 1 divided by e is something like 0.36, and in that way 1 minus 1 divided by e is something like 0.63 and somewhat. So that means in that way we can see the time constant is the time when we had a change of 63% from 0 failures to total failure. Sometimes there is a time lag before a process that degrades and fails a sample, and there are different ways in which we could understand it. That could be, for instance, you look at the failed portion of cars over time, but it is clear that cars will normally fail when they are operated. But now maybe we have an average time for which a car is in storage. For instance, it could take 3 months as an average until a car is sold. Yes, so the car is at the dealers and there it waits for the customer. And that time could be some incubation time, so the consumption of lifetime doesn't start before that. And to that purpose, Mr. Weibull found a curve which is the 3-parameter Weibull curve, which is 1 minus e to the power of t minus t0. T0 is the incubation time divided by tau minus t0. So normally when you have that knee-like curve here, you would find that suddenly at shorter times the slope goes down significantly, and that t0 could be a starting value for the analysis of T0. But now the question is how to get Weibull parameters. So we have n specimens. These will be tested, for instance, in temperature cycling tests and so on. And from these specimens, let's assume it's just 10, we write down the times when number 1, 2, 3, 4, 5, 6, 7, 8, 9, or even 10 fails. So we get 10 individual times, and these times are already written in rising order. So that's our initial table which we get from our test. Then how will we proceed with these data? There must be a small correction to the data. In order to compute the failed portion. So normally you would say when the first of 10 fails, it's 10%, second 20%, and so roughly this is true, and we can write this down. But the correct formula for f of t is it's e, so it's e minus 0.3 divided by n plus 0.4. That correction must be made according to some statistical reasons, but normally it's only relevant for the first failures, not for the majority of the failures. So here a certain correction is made. So you could say 1 minus 0.3 is 0.7 divided by 1.4, and so that's 0.5 and not 0.05 and not 0.1. Okay, but now we have the table of our failure function. And let's see how to proceed here. We have to plot it, but when we plot it on a linear scale, we will have a non-linear curve. Normally, it's always good to linearize a function, so we can see if the function or if the data are differing from the linearized behavior, and that means it is a test for the proper function. For instance, when we look at Weibull plot, we would have to plot in a way that the first percentages of failure will have a large distance on our plot, while between 40 and 70% of failure, it is plotted in a compressed way, and again at the end we have again large differences on the scale between small percentage differences. Typically, the data are plotted on a logarithmic x-axis. So, and now let us derive how this works. We have the Weibull function, and from that Weibull function we want to determine both the parameters, the tau and the beta. Okay, how can we do this? Of course, we put in the values, but when we want to know our scale, we first do linearization. So we bring the 1 to the other side, and then 1 minus f of t is e to the power of minus t divided by tau to the power of beta, and then we take the logarithm of this. When we take a logarithm of an e function, we just get the argument, so the logarithm is equal to minus t divided by tau to beta. When we want to determine beta, a good trick is to do again a logarithm. And then we have the logarithm of minus the logarithm of 1 minus f of t, and that is beta times logarithm of time minus beta times logarithm of tau. And beta times logarithm of tau is just a constant value, and the beta alone gives us the slope when we plot that double logarithm against logarithm of time. And in that way, from our transformed data, versus logarithm of time, we get the axis offset and the slope. And so we have determined both Weibull parameters. Okay. And again, an important parameter is, of course, the tau, the time constant, where we have 63.2% of failures. And the second is the slope, which is identical to the beta value. In the case of an exponential function, we can say that is beta of 1. When beta is smaller than 1, we have typically a decreasing failure rate, and when beta is larger than 1, we have typically an increasing failure rate. So, and that is typical of Weibull curve in the case of fatigue, for instance. Okay, in that way we can make a Weibull analysis on the data. We can either do it by regression, or we can do it by maximum likelihood method, but I will not go into the details of this. So let us digest this, and then we hope to proceed. So a remark. when you just learn about failures, for instance, you do registration of failing cars, then indeed you have a problem, because then you do not know the number of cars which were initially in your experiment. I just have to wait for the screen to proceed, because here I'm doing a reassignment of sound. So now another question when we look at Weibull curves is the effect of load. So as a rule, we know the stronger a specimen or a sample is loaded, the more it will be degraded, and that means the earlier it fails. On the other hand, when it is for instance, here we have a Weibull curve for automotive electronics in field. So, and maybe we make a design that a significant portion of failures will just appear after 10 years. Let's say 1% of failures starts at year 10, and that's the Weibull curve, and for instance, a typical slope would be something between 3 and 5. Okay. Now we want to make sure that our automotive electronics will reach this, and that must be proved in some way. And of course, it is not possible that you test for 10 years, and also you cannot test for 10 years with 1,000 cars. So then your car would be outdated by the time you are finished with testing. So what do you need then? Of course, it is accelerated testing. And how do you accelerate a test? That can only be done by stronger loading. So give the part more stress and it will fail earlier. The question now is, how much stress do I have to give to my specimen, and which transformation curve can I use in order to predict or extrapolate my lifetime, or to extrapolate my Weibull curve. To that purpose, I would build a certain sample which is tested, and it is tested in a way that it fails early. it is important that the failure mode does not change between field conditions and accelerated test conditions. And a relatively easy way of testing for this condition is when the slope of the Weibull curve is the same. That's a good hint that you still have the same failure mechanism. But you must not extrapolate between different failure mechanisms. So you could say you have a failure of a mechanical part, and on the other hand you have failure of an electrical interconnection. One is for high load, the other is for low mechanical load, and you cannot extrapolate between these. Now, what is the load? That can be quite different. We can either consider load on a system level for, it could be the speed at which we drive, or it could be its effect on the material. For instance, if you have an electro vehicle and you drive faster, you also will have higher temperatures in your semiconductor. And now let's, in this case, just take temperature as the load. On the other hand, if you drive more speedy, also accelerations as a result of vibrations, for instance, will be higher, and that means more load. Okay, in that way, you can do the testing, but in that case, you still just know the load is high curve, but not the load is low field curve. And now we must look, how do we come to that extrapolated curve? Okay, we have temperatures, acceleration, vibrations, and also forces, mechanical stresses or mechanical strains can be load parameters. In some cases we use delta T. We can also use voltages or currents as parameters for load. The J here is the current density, which is also an important parameter. And when we divide the voltage by a certain thickness of a material, we typically get a field strength. And that is important, for instance, for dielectric breakdown. Okay, still we do not know the Weibull curve for our electro vehicle in the field, and now we must get to a method how to predict this. What do we need for this? Here we need a mathematical failure model. And my question is, what is the most simple failure model on the basis of which we can compute such an extrapolated curve? Of course, the relation between two curves is the so-called acceleration factor, or in German also Raffungsfaktor. So, how do we get such a factor? Here it is important that you think about certain failure models. And now let's regard the different stress parameters. So, for instance, when temperature is regarded, we have the so-called Arrhenius curve. Of course, every engineer should know it. And the Arrhenius function says the failure rate is some basic failure rate times e to the power of minus activation energy divided by kT, and EA is the activation energy measured in electron volts divided by kT, where K is the Boltzmann constant and T is the absolute temperature measured in Kelvin. The engineers typically often use the activation energy in joule per mole, and in that way it is divided by the gas constant R. When you do a standard acceleration model, you often use an activation energy of 0.7 electron volt or sometimes of 1 electron volt. 1 electron volt doubles the failure rate between 120 degree and 130 degree by the increase of 10 degree Kelvin or centigrade. Again, the acceleration factor is just the relation between two failure rates, or you could write it on the basis of the Arrhenius curve. It's e to the power of minus EA divided by KT1 plus EA divided by KT2. Of course, it still has to be proved that this acceleration factor is really valid, because in real life such activation energies vary between 0.3 electron volt and something like 3 electron volts. That means the acceleration factor which you computed is a severe uncertainty in your lifetime prediction. On the other hand, you can try to do the following. You do tests at several conditions which are close together, and from these tests, like from the left black curve and the blue curve, you get parameters like the activation energy. And in that way, you will be able to determine activation energies which are valid for your part, and in that way, the activation energy will have a higher quality, and your acceleration factor will also be of higher validity than when you use standard acceleration parameters. Okay, thank you for your attention.